Maybe it'll help if I rewrite this a little bit. So x1 is true for x2 also, but let me just rewrite this one. So x1 is equal to y over a, all raised to the 1 over alpha 1 plus alpha 2, times alpha 1 over alpha 2, w2 over w1, all raised to the alpha 2 divided by alpha 1 plus alpha 2. So I'm asking about what happens as we increase y. We don't have to worry about this part. This is all, we're holding this constant right now for this little experiment. So what happens as we increase, what happens to input demand for input 1 as we increase y? It'll increase. At what rate will it increase? Let me show you the formula, sorry. What rate will it increase? Depends on these parameters, alpha 1 and alpha 2. Okay, what if we have constant returns to scale? Yeah, so if we have constant returns to scale, with this Cobb-Douglas production function, that means that alpha 1 plus alpha 2 is equal to 1. So that means that input demands are going to be linear. They don't necessarily have a slope of 1, because we don't know what a is and that other stuff, but it'll be a linear function. It'll start at 0, so this will be the input demand if we have alpha 1 plus alpha 2 equal to 1. Okay, so the phrase constant returns to scale should sort of be a tip-off here. This is, if scale increases, that means we're going to increase y, and look, this is a constant slope. Okay, what if we have increasing returns to scale? So with increasing returns to scale, alpha 1 plus alpha 2 are greater than 1. And so that's right. So we'll get something which will start at 0, but it'll increase at a decreasing rate. So this is something like this is the case for alpha 1 plus alpha 2 increasing greater than 1. There we go. And then we got one case still to consider. If alpha 1 and alpha 2 are, if they're less than 1, we have decreasing returns, and so as you guess, we'll get something like that. So let's just take this last one and interpret it. With decreasing returns to scale, what this says is the larger the scale at which the firm operates, the higher, the more rapidly the input demand for x1 increases. So you operate at a very high scale, you're going to be relatively inefficient in a way compared to if you were operating at a very low scale. All right. So I've got another experiment I want to do here. This involves changes in prices and quantities. Let me draw it this way. So this is a Marshallian input demand function. So we're going to have prices W1 on the vertical axis and quantities of x1 demanded on the horizontal axis. What will that function look like? So here, for this experiment, we're holding y fixed. This is just going to be a constant. So all the action is going to be here, in fact, for x1. So let's see. Well, what if w1 is equal to 0? What will x1 be equal to? We put a 0 here in this denominator. Then we'd have infinite demand for that input, or it's not defined really. But so let's make it a very small positive number. It'll be big. What if w1 is very large? Then it'll be very small. Okay, so we know we're going to have a point up here on the function and a point over here. How do we connect them? Yeah. Okay. So I like that. You know, we've got something. This is another sort of hyperbola because the variable changing only shows up in a denominator. So this might be a sort of hyperbola. It does something like this. This is the input demand for x. It's a function of its own price. Okay. You can see that demand for x1 also depends on demand for w2, though. So how does demand for x1 depend on w2? Yeah, that's right. So okay, good. Yeah. So as w2, so what's the direction here? As w2 gets big, what happens to demand for x1? Yeah, so this is increasing. Demand for x1 is increasing in w2. I'm going to switch these around just a little. Let me put w2 here and x1 here. So if w2 is 0, then demand for x1 is 0. And as w2 increases, demand for x1 is increasing. What's the rate at which it will increase? Yeah, so here we have a case, unlike this case, where everything hinged on whether alpha 1 plus alpha 2 is greater than 1 or not. Here, the critical exponent is this alpha 2 over alpha 1 plus alpha 2. And so this, by construction, has to be less than 1. And so as a consequence, what we'll get for an input demand, this sort of cross input demand function, how x1 depends on w2, is going to have this kind of shape. It'll be a concave function. Okay. All right, good. Okay, so questions about input demands before we go on? Okay, let's keep going now. So we've got input demands. Let's go ahead and we're going to get now what we started looking for, which is the cost function for the firm. So we're trying to solve the cost minimization problem today, and the outcome for that is going to be this function, which says what the minimum cost actually is if the firm has to produce y and faces prices w. So the way you compute that in general is given on this slide. What you do is you take the input demands, and this is exactly analogous to the way you guys did the consumer expenditure minimization problem. What you do is you take these factor demands and plug them into the objective function for the cost minimization problem, and then you get a function which depends only on the price of w and the output y. And that tells you what the minimum cost way to produce output y given price of w is going to be. All right, so is that approach clear? Okay, so with that general thing in mind. Oh, by the way, we're talking about these factor demands here, and we've noticed that there are analogies between the firm's problem and the consumer problem. What are these input demands analogous to in the consumer problem? And they're analogous not to Marshallian demands, but instead to Hicksian demands, exactly. Where they call the arguments for the Hicksian demands, where prices the consumer faced and the level of utility they need to achieve. Here, the arguments for the input demands are the prices the firm faces and the output that the firm has to produce. So they're analogous to Hicksian demands. Okay, so with that, let me go ahead and work out what the. Oh, let's see, I did this poorly. Let's go ahead and compute the firm's cost function. So my method here is going to be what's described on the board. Namely, I'm going to want to substitute these expressions for x1 and x2 that we've got into the cost minimization problem. So for this example, we'll have c of y w equal to w1, and we can plug in x1 here. So it'll be y over a to 1 over alpha 1 plus alpha 2 times alpha 1 over alpha 2, w2 over w1, all raised to the alpha 2 over alpha 1 plus alpha 2. So that's the, what have I written so far? What is this? Yes, it's the firm's expenditures on input 1. They also have to pay for input 2, so that'll be plus w2 times y over a, all raised to 1 over alpha 1 plus alpha 2, times alpha 2 over alpha 1, times w1 over w2, all raised to the alpha 1 over alpha 1 plus alpha 2. And so that's one expression for the firm's cost function. We can do a little bit better than this. This thing is, it's not actually a terrible expression in a way. It's easy to interpret each one of its parts. But we can simplify it a little bit. Any thoughts about what we could do here to make this a little more compact and interpretable? Yeah, very good. So one sort of thing we can immediately spot is that we have y over a raised to a common exponent both here and here. So that's definitely true. We can factor that thing out. Let's see, what else can we do? I'll just do that first. So we'll have this equal to y over a, all raised to 1 over alpha 1 plus alpha 2. And then we'll have another trick we can do is to factor these w1 into this expression and factor w2 into this expression. And so that's going to give us alpha 1 over alpha 2 times, let's see, so how many do we have here? I want you to, I guess what we could say is that we're going to get, in case I'm worried about my notes, let's see. Well, this part will have alpha 2 over alpha 1 plus alpha 2, plus the w's will have w2 to the alpha 2, or this way, w2 to the alpha 2 over alpha 1 plus alpha 2, and we'll have w1 to the alpha 2 all over minus alpha 2 over alpha 1 plus alpha 2 minus 1. There we go. And we'll have something similar here. We'll have alpha 2. Okay, who said that first? Is Scott responsible? You're the only person I see getting credit from somebody else. Right. Yeah, okay, Jeff, could you give Scott, mark down Scott for an extra credit point? Thank you. Okay, thanks. Yeah, there should be w1 here. Okay, so then we'll have alpha 2 over alpha 1 2 plus.
So w1 should be a plus 1 on the first part. Where it says w1 to the negative alpha 2 over alpha 1 plus alpha 2 plus 1.
Oh, you're right. Thank you. Okay, so who said that one? That was. Okay, if this degenerated. Okay, so what's your name? Kevin. So can you arrange for Kevin to get an extra credit point too? Okay. I hope this doesn't degenerate into a melee, but that's good work, guys. Thanks. Let's keep going. So alpha 2 over alpha 1, yeah, that should be a plus 1. I'm going to go ahead and simplify this because it's crying out for simplification. Minus alpha 2 over alpha 1 plus alpha 2 is equal. I'll lay this on the side. It's simply going to be equal to alpha 1 over alpha 1 plus alpha 2. So let me go ahead and just plug that in here, okay? There we go. And you can start to see some beauty emerging here, I think. And we're going to get something similar over here. In particular, we should wind up with alpha 2 over alpha 1 to the alpha 1 over alpha 1 plus alpha 2. That's all this bit. And then we'll have w1 raised to the alpha 1 over alpha 1 plus alpha 2 times w2 raised to the alpha 2 over alpha 1 plus alpha 2. Okay, and I can tell this is correct because it's beautiful. Except I need that closing bracket. And so now, this is really nice. Look, I got these terms involving the w's here, and they're identical, so I just factor them out. So this is all equal to y over a, 1 over alpha 1 plus alpha 2. I'm going to set these alpha terms aside for a moment and factor out the w's. We'll have w1 to the alpha 1 over alpha 1 plus alpha 2, w2 alpha 2 over alpha 1 plus alpha 2, so there's the w's, and then times a term which is only going to depend on the alphas. So I'll have alpha 1 over alpha 2 raised to the alpha 2 over alpha 1 plus alpha 2 plus alpha 2 over alpha 1, all raised to the alpha 1 over alpha 1 plus alpha 2. This function here, since it only depends on these constant alphas, I'm going to give it a name. I'm going to call this this little function h of alpha. But it's a constant. It just depends on the alphas. And so this is our cost. Let me go right out with that simplification. So c of y w is equal to y over a. I'm going to write it this way. w1 to the alpha 1, w2 to the alpha 2. This whole thing to the 1 over alpha 1 plus alpha 2 times this constant h of alpha. And we're done. So this is the cost function for the Cobb-Douglas case. Yes?
So is h of alpha one of the things we're going to have to worry about?
Well, so we didn't have to worry. The answer is depends. We need to worry about it more than we did in the consumer case. In the consumer case, we want to have a constant like this for the indirect utility function, for example, and we could sort of usually ignore it there because utility, we don't care what the units are really. We just need to be consistent. Here, this is measured in dollars, and so the number of, or whatever the units of the prices are, it's measured in dollars. And the firm certainly cares about dollars, so we should be careful before just ignoring this guy altogether. For a lot of cases, it's not going to matter. You can see if you're considering two different cost functions or prices change, for example, and you're looking at the ratio, this thing will cancel out. So it'll often go away, but in general, we certainly do need to keep track of it. Okay. All right. It looks to me Well, that's a good stopping point. So let's stop there. Do take a quick look before next time at the Cylindra wiki page. I'm going to give a little example here next time. Yeah.